A thin, pale haze drifts across the darkness, so faint it almost disappears when you try to look directly at it. Stars are scattered loosely, too loosely, as if gravity forgot to finish the job. Their light barely gathers enough strength to push through the cosmic night. You float inside this vast, ghostly structure, and only after several moments does it reveal itself as something astonishing. A galaxy. A galaxy so diffuse, so spread thin across hundreds of thousands of light years, that the universe seems to have sketched it in pencil instead of ink. Nothing here feels solid. The starlight is diluted, stretched across a space normally reserved for systems far more luminous. What should be a dense, swirling congregation of hundreds of billions of stars looks instead like the remains of one, its components scattered loosely and left to drift without urgency or pattern. The void between each star is immense. Even the core, where brightness usually rises as stars cluster tightly around a supermassive black hole, appears barely brighter than the outer edges. This entire structure seems to hover on the edge of non-existence, a cosmic mirage made of sparse stellar embers. The faintness isn't your imagination. Ultra-Diffuse Galaxies, UDGs, are among the lowest surface brightness objects ever classified as full-fledged galaxies. Their light is spread so thin that if you placed one where the Milky Way is, you could look straight through it and still see the Virgo cluster beyond. Their surfaces often have brightness values around 24 to 26 magnitudes per square arc second, which, in practical terms, is so dim that even long-exposure telescopes struggle to distinguish the galaxy from sky noise. They are the cosmic equivalent of smoke drifting in a breezeless room, present but barely, yet their dimensions are anything but small. Many UDGs stretch to roughly the same diameter as the Milky Way, about 100,000 light-years across. A typical one might span 80,000 light-years or more, translating to about 950 billion kilometers or roughly 590 billion miles. Their size is familiar, but their content is not. While the Milky Way hosts around 100 billion stars, a UDG may possess only a few hundred million, sometimes even fewer. Imagine inflating a balloon until the air thins so much you can almost see through it, yet the balloon remains gigantic. That is the visual and physical contradiction of these ghostly systems. As you drift farther into the structure, each star comes into view like an isolated lantern suspended in a great mist. Few appear clustered, most are solitary, spread out over distances far larger than in typical spiral galaxies. If the Milky Way's stellar neighbourhoods resemble tightly packed suburban blocks, a UDG resembles a sparsely populated countryside stitched together by long stretches of empty land. This thinness raises a profound question. How does a system this fragile stay together? Gravity should have an easier time in a more compact galaxy. When stars gather tightly, their combined mass reinforces the structure. But in an ultra-diffuse galaxy, the mass is stretched across such great distances that it seems the system should fall apart under the slightest disturbance. Yet many of them do not. They drift, mostly intact, through galaxy clusters flooded with gravitational tides strong enough to shred ordinary dwarf galaxies. And that simple fact, this improbable survival, is one of the reasons ultra-diffuse galaxies force astronomers to rethink how galaxies form and persist. UDGs challenge assumptions at the most basic level. The assumption that size should correlate with brightness. For decades, astronomers believed that large galaxies required enormous populations of stars, gas, and dust. A Milky Way-sized footprint meant Milky Way-like luminosity. When faint smudges appeared on photographic plates, astronomers often dismissed them as imaging artifacts, wisps of galactic cirrus, or small galaxies blurred by poor focus. The idea that a full-size galaxy could shine at the brightness of a small dwarf seemed too extreme. Yet here you are, drifting inside one, and it is unmistakably real, a sprawling, ghostly presence with mass distributed across a structure too faint to catch the eye. Modern astrophysics describes galaxies in part by their surface brightness, how much light reaches each square arc-second of sky. Ultra-diffuse galaxies fall into the extreme end of this spectrum. For many, the most luminous regions barely exceed the brightness of the night sky itself. If Earth had a sky free of light pollution and one of these galaxies were placed nearby, you could stare right at it and still see nothing but stars. It takes long exposures, clever telescopes, and sensitive detectors to tease these structures out of the background. And once we learned to see them, we discovered they are not rare. They are scattered throughout clusters like Coma and Virgo, hidden in plain sight. Ghost giants, drifting behind the brighter swarm of typical galaxies. But what makes them truly interesting isn't just their faintness or size, it's what their existence implies. Some UDGs appear to be galaxies that simply failed to form stars efficiently, expanding outward before their gas could collapse into dense clusters. Others may be dwarf galaxies inflated by tidal interactions, stretched until they became huge and faint. A few seem to have extraordinary amounts of dark matter, suggesting that they occupy massive halos far larger than their complement of stars would indicate. And then there are the controversial exceptions, galaxies that appear to lack dark matter entirely, contradicting the standard frameworks of galactic evolution. The reality is that no single explanation fits them all. UDGs are not one type of galaxy, but several different stories wearing the same faint disguise. Some are relics of violent interactions, some are quiet survivors of harsh cluster environments, and some might be evolutionary failures frozen at the wrong moment in cosmic history. Their diversity is as remarkable as their dimness. Returning to the view around you, the ghostly structure becomes even more remarkable the longer you look. Dust is almost absent, gas is minimal, the starlight flickers weakly, elderly and sparse. It feels like a fossil, an imprint of a galaxy that tried to grow but never became luminous enough to reveal itself to the universe. And yet, despite the lack of brilliance, despite the fragile architecture, it persists, bound by forces that resist disappearance. Before we step further into the scientific maze surrounding these spectral systems, there's a moment of quiet worth taking. If you enjoy exploring these faint and extraordinary corners of the cosmos, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow and it keeps these journeys alive. This drifting haze is just the beginning. Ultra-diffuse galaxies are not mistakes or anomalies. They are chapters of cosmic evolution written in near-invisible ink. And their presence forces us to confront a deeper truth. The universe does not owe us visibility. Some of its most intriguing structures exist at the threshold of perception, waiting for the technology and the curiosity to finally reveal them. The first hints appeared long before anyone knew what they were looking at. In the late 1970s and early 1980s, while most astronomers were focused on bright spirals, elliptical giants, and easily classifiable dwarf galaxies, a few peculiar shapes began surfacing on deep photographic plates. These weren't elegant spirals or compact dwarfs. They weren't even obviously galaxies. They looked like faint, irregular smudges, barely distinguishable from the natural grain of the photographic emulsion. Anyone could be forgiven for assuming they were defects, light leaks, dust on the plate, or accidental overexposures. After all, the outer regions of photographic film often produced uneven textures, and the night sky's faint glow produced gradients that sometimes imitated diffuse features. But the strange thing was that the smudges occasionally appeared in more than one exposure. Astronomers developing plates from the Coma cluster, a dense and sprawling environment rich with galaxies of all types and sizes, began to notice that certain diffuse patches showed up consistently in multiple observations. They weren't bright enough to draw attention, yet they were persistent enough to invite curiosity. Still, in an era where data reduction meant manually inspecting plates under red lights, no one wanted to spend precious observing time chasing what could easily be optical ghosts. The priority was to understand luminous galaxies, the ones shaping the dynamics of clusters, the ones whose evolution was central to the cosmological questions of the time. A faint blur with no obvious structure simply didn't justify precious telescope time. The scientific culture of the period also worked against deeper investigation. Galaxy evolution was still built on the assumption that large disks required substantial stellar mass and therefore should be bright. If a galaxy appeared extremely faint, the default assumption was that it must be physically small. Something the size of the Milky Way but shining like a weak dwarf simply didn't fit the frameworks then in use. So smudges that looked enormous but barely luminous were inconsistencies to be filtered out, not phenomena to be understood. The problem was amplified by the technology itself. Photographic plates, for all their historical importance, were notoriously insensitive to low surface brightness structures. Unlike digital detectors, which can accumulate photons over long periods with exceptional linearity, film has a limited dynamic range. Bright objects register cleanly, faint ones fade into grain. A large galaxy whose total luminosity is spread thinly across a wide area becomes nearly invisible, its brightness smeared out until it looks like a diffuse background glow. Even if such a galaxy were present, detecting it required a combination of luck, long exposures, and ideal sky conditions, none of which were guaranteed. As low-surface brightness astronomy began to develop slowly through the 1980s and 1990s, driven by pioneers like David Malin at the Anglo-Australian Telescope, it became clear that the universe was hiding a population of faint structures just beyond the reach of standard observing methods. Malin's specialized photographic amplification techniques revealed giant low-surface brightness disks, extended halos, and diffuse tidal features that had previously gone unnoticed. But even his advanced methods struggled to reveal the extremely dim, extremely extended galaxies that would later be classified as ultra-diffuse. At the same time, theoretical developments were hinting that many galaxies might not form stars efficiently. Supernova feedback, environmental quenching, and inefficient cooling in low-mass halos were all capable of producing large, faint objects. But there was a gap between theory and direct observation. Models could suggest that faint, enormous galaxies might exist. The sky remained stubbornly ambiguous. By the late 1990s, CCD technology had finally begun replacing film. Digital detectors, unlike photographic plates, have predictable noise properties, excellent low-light sensitivity, and the ability to integrate over long exposures without saturating. This shift was a revolution for astronomers studying the low-surface brightness universe. But at the time, telescope time remained focused heavily on bright, well-defined targets. Massive surveys like the Sloan Digital Sky Survey, SDSS, were optimized for mapping millions of galaxies efficiently, not for detecting faint, diffuse ones. SDSS exposures were short, just enough to capture galaxies with typical brightness, but insufficient to catch the nearly invisible bodies hovering at the edge of detectability. Still, hints accumulated. Astronomers like Peter van Dokkum, who would later play a central role in the UDG story, began conducting deep surveys of galaxy clusters and low surface brightness environments. But even then, the faint structures they detected were ambiguous. They often appeared to have no well-defined boundaries, no clear cores, and no obvious spiral or elliptical morphology. Distinguishing a genuine galaxy from a combination of background noise and scattered light was extremely difficult. In some cases, diffuse patches could be caused by bright stars just off the field of view, their halos blending into the background. atmospheric scattering, reflections inside the telescope optics, and even the faint glow of the night sky could imprint shapes that vaguely resembled astronomical objects. The skepticism was understandable. Astronomy had been haunted for decades by illusions, false detections of canals on Mars, phantom nebulae, and clusters that vanished upon re-examination. Accepting a faint, structureless smear as a galaxy required confidence that few researchers were willing to risk their reputations on. Low surface brightness astronomy was also still developing its theoretical motivations. While there were solid reasons to believe faint galaxies might exist, astrophysics tends to focus where the data are richest. Bright galaxies produce measurable spectra, clear morphologies, and high signal-to-noise photometry. UDGs offered none of these benefits. Their low stellar density made spectroscopic follow-up nearly impossible with the instruments of the time. Without spectra, astronomers couldn't determine distances, redshifts, or velocities, and without distances, you could not tell whether a faint patch was a giant, distant object or a nearby dwarf. This ambiguity was fatal for classification. A diffuse object could be interpreted in multiple ways, and the path of least resistance was always to assume it was not a galaxy. In fact, many astronomers simply labelled such features as galactic cirrus, faint clouds of dust within the Milky Way illuminated by scattered starlight. Cirrus is notoriously deceptive, able to imitate large, ghostly structures with soft gradients and uncertain boundaries. Unless a diffuse patch had embedded point sources clearly belonging to a distant stellar population, it was far easier to assume it was cirrus than a new class of galaxy. Meanwhile, scattered research groups continued accumulating suspicious detections. Some low-surface brightness dwarfs were confirmed in the field. A few enormous faint disks were verified around large spirals. The universe seemed increasingly willing to reveal structures that defied the classification systems built during the mid-20th century. But the catch was always the same. These discoveries required long exposures and telescopes willing to trade survey speed for depth. That kind of observing strategy was not yet mainstream. By the early 2000s, astronomers began to suspect that galaxy clusters might contain a hidden population of extremely faint galaxies, objects too spread out and too dim to show up in most wide-field surveys. The Coma cluster, being massive and relatively nearby, was an obvious place to hunt. Teams, including Van Dockum and colleagues, began pushing CCD imaging deeper, using long exposures and specialized reduction techniques to limit noise and reveal faint structures. Their detections grew more compelling. Not just ambiguous smudges anymore, but faint objects with hints of elliptical shapes, small central concentrations, or even star clusters embedded within them. These emerging clues pointed towards something unexpected, large, diffuse galaxies that were real, physical systems, not artifacts, not dust, not reflections. Yet progress stalled because the evidence remained frustratingly weak. A CCD detector could capture the faint glow, but confirming these smudges as galaxies required follow-up observations with large telescopes capable of spectroscopy. And the simple truth was that UDGs were too dim for standard spectrographs. To measure a redshift, you need light, a concentrated amount of it. A galaxy whose brightness is spread across tens of thousands of square light-years doesn't give you that. In effect, they were detectable but not verifiable. Astronomers were staring at the footprints of something significant, but lacked the tools to follow them. The skepticism persisted. Even Van Dockum's early work was met with caution. These faint shapes could still be cirrus, noise, or distant background galaxies smeared by interpolation algorithms. Without confirmation, the scientific community largely held back. Nobody wanted to declare a new class of giant faint galaxies based on images that looked like someone had breathed gently on the detector. What the field needed was not just better images, but a fundamentally different kind of instrument, something designed from the ground up to hunt low surface brightness galaxies. A telescope that could gather the whisper-quiet light from diffuse structures without scattering, aberrations, or internal reflections hiding them. And in 2014, that instrument finally appeared. But long before the breakthrough came, the stage had already been set. For nearly 3 decades, astronomers had been circling around these pale shapes, dismissing them, glimpsing them again, doubting their reality, and occasionally suspecting that something extraordinary was hiding behind the noise. Those faint smudges on photographic plates weren't imperfections. They were galaxies, vast, ghostly, almost invisible, and they had been waiting for the right eyes to finally recognize them. Nighttime at New Mexico Sky's observatory is usually quiet, but in late 2014 it hosted something that didn't look like astronomy at all. Instead of a dome housing a massive mirror or an optical tube taller than a person, the installation resembled a cluster of oversized photography lenses mounted together like the compound eye of an insect. No single lens was large, none looked impressive on its own. But that was the misdirection. An intentional one, because this odd structure, the Dragonfly Telephoto Array, was about to reveal an entire population of galaxies the universe had been hiding for decades. Dragonfly wasn't conceived for beauty shots of nebulae or close-ups of planets. It had a singular purpose: to detect objects so faint, so spread thin across the sky, that standard observatories missed them completely. And the reason for that blindness wasn't a lack of sensitivity, but a more insidious problem: scattered light. Every telescope mirror, no matter how finely polished, scatters a small amount of light internally. Bright stars, reflections off baffles, imperfections in coatings, and micro-roughness in the optical surface all contribute to faint halos around objects that shouldn't have halos at all. For almost every field of astronomy, this is harmless. For low-surface brightness astronomy, it is catastrophic. A galaxy whose entire structure glows only slightly above the background sky can be completely erased by the internal scattering of the telescope observing it. Traditional telescopes excel at detail. Dragonfly's mission was to excel at darkness. Peter van Dokkum and Roberto Abraham realized that modern telephoto lenses, with advanced nano-coating technologies developed for consumer photography, actually controlled scattered light far better than professional observatory optics. Lens manufacturers like Canon had perfected sub-wavelength nanostructures on the inner lens surfaces that reduced reflections to nearly zero. These coatings were originally designed for wildlife and sports photography to cut down on lens flare and internal reflections. But in astronomy, they opened an entirely new observational window. The result was a telescope with unparalleled purity of darkness. Each lens in the array was equivalent to a small refractor with an extremely clean point spread function. When dozens of these lenses were combined and their images stacked, Dragonfly reached surface brightness limits no single large telescope could approach, not because it collected more total light, but because it collected cleaner light. It wasn't the brightness of the object that mattered, it was the absence of contamination. For the first time, astronomers had an instrument optimized not for bright things, but for faint ones. Dragonfly began scanning the Coma cluster, already known for its density, complexity, and chaotic gravitational environment. The cluster sits roughly 320 million light-years from Earth and contains thousands of galaxies. It is one of the first clusters studied in the history of extragalactic astronomy, with deep exposures dating back to the 1950s. Yet, in all those decades, nobody had seen what Dragonfly saw. The images that started coming in were quiet at first. Deep fields with fine grain, faint halos, and very little of the typical scattered light glow. Dragonfly's early exposures looked almost too clean, almost unnatural, as if the sky had been scrubbed. But as the team processed the data, diffuse shapes began emerging, not small ones but huge ones. Pale, ghostly systems as large as the Milky Way, but nearly invisible. They weren't flukes, they weren't artifacts, they weren't cirrus, they were real galaxies. Overnight, the smudges that had haunted photographic plates for decades were revealed as an entire population of ultra-diffuse galaxies, UDGs, living inside Coma. Some stretched over 100,000 light-years across, comparable to our galaxy's diameter, but contained only a fraction of the stars. Their light was so thinly spread that they skirted the edge of detectability. A typical UDG in coma has a central surface brightness fainter than 24 magnitudes per square arc second. Some dip toward 26. To put that in perspective, a person standing on Earth's surface with perfect vision, looking up at a UDG placed just outside the Milky Way, would see nothing but empty sky. Even sensitive telescopes would mistake the galaxy for background noise unless specifically designed to suppress scattered light. As Dragonfly's survey continued, more and more UDGs appeared, each one a whisper of starlight stretched across a space large enough to host an entire spiral galaxy. The team announced the discovery of 47 such galaxies in 2015, but as observation strategies improved, the number grew dramatically. Later estimates suggested there could be hundreds, possibly over 1,000 UDGs in coma alone. This was not a rare curiosity. This was a hidden population. The discovery shocked astronomers because it violated several comfortable assumptions. Galaxy brightness had always seemed tightly linked to galaxy size. Larger galaxies contain more stars produce more light. But these ghost giants broke that rule. They had the size of a major galaxy, but the luminosity of a small dwarf. Some were incredibly diffuse, with stellar densities hundreds of times lower than the Milky Way's. They were cosmic apparitions, huge but faint, structured but nearly invisible. The question instantly was, how did they survive? Coma is a harsh environment. Galaxies plunge through its gravitational fields at speeds of thousands of kilometers per second, often 2,000 to 3,000 kilometers per second, or about 1,200 to 1,860 miles per hour. Tidal forces within the cluster should tear fragile systems apart. A galaxy with stellar material spread thinly across such a large area should be shredded within a few orbits. And yet, many UDGs showed no signs of disruption. They appeared intact, stable, and enduring. The only way a galaxy that faint could survive inside coma is if its dark matter halo were enormous, massive enough to hold the structure together against the cluster's gravitational assaults. Some UDGs, like Dragonfly 44, appeared to have dark matter fractions so large they rivaled the Milky Way. Their visible stars were almost irrelevant. The halo was the true galaxy. Dragonfly forced astronomers to confront a remarkable possibility. The universe might be filled with galaxies that look empty, not because they lack gravitational scaffolding, but because they failed to form stars efficiently. These are not failed dwarfs. Some may be failed giants, massive halos that never ignited into bright spirals or ellipticals. All of this was only possible because Dragonfly could see deeper into darkness than any previous instrument. The secret was its nano-coated refractor lenses. By eliminating internal reflections, Dragonfly achieved an ultra-clean point spread function that pushed surface brightness detection into uncharted territory. Normally, imaging a faint diffuse object requires extremely long exposures, but even long exposures can be ruined by scattered light. Dragonfly didn't just integrate photons, it protected them. It used multiple small lenses instead of one large mirror, avoiding mirror microscattering entirely. Each lens contributed a small, pristine piece of the sky. Stacking dozens of these pristine images produced a combined view with almost no optical contamination. For the low-surface brightness universe, this was nothing less than a revolution. The array grew over time, from 8 lenses to 24 to 48. Each expansion improved depth and signal-to-noise with modular simplicity, and because the system used commercially available lenses, scaling it was far cheaper and more flexible than building a new conventional telescope. The deeper Dragonfly looked, the stranger the sky became. It revealed tidal streams stretching hundreds of thousands of light-years, ghostly halos around normal galaxies, faint remnants of past mergers, and vast, diffuse structures that traditional observing had overlooked. But the ultra-diffuse galaxies were the headline. They were not mere features. They were whole galaxies hiding between the cracks of detectability. Surface brightness is one of the most unforgiving frontiers in observational astronomy. A galaxy can be incredibly massive, yet rendered invisible if its stars are too spread out. The night sky itself, even at high altitudes and in perfect conditions, glows faintly. Air glow, zodiacal light, scattered starlight, and atmospheric diffusion all combine into a brightness floor. If a galaxy's glow is below that floor, it becomes indistinguishable from the background, no matter how many photons it emits in total. Dragonfly finally pushed below that observational floor. It could identify structures at surface brightness levels previously considered unreachable. It could separate faint halos from scattering artifacts. It could map the outskirts of galaxies with astonishing clarity. For the first time, astronomers could confidently say, if an enormous, faint galaxy existed, Dragonfly would see it. And it did, over and over again. The COMA discoveries were only the beginning. Dragonfly later revealed UDGs in the Virgo cluster, in field environments, and even local examples much closer to the Milky Way. Some were quiescent, some still forming stars, some rich in globular clusters, some nearly empty. Each one expanded the puzzle. UDGs were not a flaw in the data, they were a flaw in our expectations. Before Dragonfly, the universe looked bright, well-structured and catalogued. After Dragonfly, it looked incomplete. Invisible populations lurked between the luminous ones. The cosmos wasn't just hiding faint galaxies, it was hiding entire evolutionary pathways. All of it discovered not by building a larger mirror, but by thinking differently about light, by eliminating the glow we once assumed was unavoidable, by making a telescope that embraced darkness instead of fighting it. The Dragonfly Telephoto Array didn't just reveal ghost galaxies. It taught astronomers that the universe is far dimmer and far richer than we ever imagined. If you were to drift toward an ultra-diffuse galaxy from a great distance, the first thing you'd notice is how deceptively normal its outline appears. Many have diameters comparable to the Milky Way. On paper, the numbers line up neatly, a span of roughly 80,000 to 100,000 light-years from one faint edge to the other, matching the broad scale of our home galaxy. But as you approach, the illusion dissolves. The structure looks hollow, thin, almost underdeveloped, as though the lights of an entire city had been reduced to a handful but stretched across its full metropolitan footprint. It is a galaxy drawn to full scale, but only lightly inked in. The Milky Way contains on the order of 100 billion stars. Ultra-diffuse galaxies, despite their similar physical dimensions, typically host only a few 100 million. Some have even fewer. Spread those stars across a disk the size of the Milky Way, and the average stellar density plummets. In many UDGs, if you travelled through them as you would through our galaxy, the night sky would look strangely empty. The stellar density we take for granted, bright star fields, clustered regions, the dense glow of the galactic plane, would be replaced with wide intervals of darkness and only occasional points of light. This profound thinness is why they remained hidden for so long. Our instruments were built around a set of assumptions that worked well for traditional galaxies. Large galaxies should be bright, and small galaxies should be faint. That correlation made sense for decades. When astronomers found faint objects on images, they assumed they were dwarfs, small systems containing few stars. An object as large as the Milky Way but shining at the brightness of a small dwarf simply did not fit the established framework. Ultra-diffuse galaxies break this intuition entirely. Their diameters tell one story, a large gravitational structure with space enough for a thriving stellar population. Their luminosity tells another, a system with only a tiny fraction of the stars expected for its size. Consider the Milky Way again. Its disk, viewed from afar, would show a strong central bulge, clearly defined spiral arms, star-forming regions glowing with fresh blue stars. dust lanes carving dark silhouettes across the starlight, and a steep gradient in brightness from centre to outskirts. A UDG, by contrast, exhibits almost none of these features. Their light profiles are shallow. Their central regions barely rise above the brightness of their outskirts. Their structures are smooth, diffuse, and almost textureless. Surface brightness is the clearest way to express this. Many UDGs have central surface brightness values fainter than 24 to 26 magnitudes per square arc second. That puts them at the very threshold of what even modern telescopes can detect. If you placed one of these galaxies just outside the Milky Way and looked up from Earth, even with perfect dark skies, you would see no glowing band, no bright core, no obvious hint of a galaxy at all. Just a few sparse stars quietly scattered across a region that otherwise resembles empty sky. Why are they so empty? One idea suggests that UDGs represent galaxies that forgot to form stars, an evocative phrase that captures a genuine astrophysical process. For a galaxy to build a luminous stellar population, gas must cool efficiently, collapse inward, and reach densities high enough to trigger star formation. If that process is interrupted early by supernova feedback blasting gas outward, by heating from the cosmic ultraviolet background, or by internal turbulence, star formation becomes inefficient. A galaxy may grow spatially, but without enough dense gas to sustain stellar birth, it remains dim. Another possibility involves angular momentum. Galaxies forming inside dark matter halos with unusually high spin can spread their gas over large radii. With the gas diluted, densities remain too low to ignite robust star formation. The result is a galaxy with the footprint of a giant, but the luminosity of a dwarf. In dense environments like the Coma cluster, some UDGs may have been shaped or reshaped by tidal forces. Galaxy-galaxy encounters can stretch, heat, and redistribute stars. A once compact dwarf may be puffed up into a wide, faint structure. Ram pressure stripping from the hot intra-cluster medium can remove gas and quench star formation, leaving behind a large, diffuse stellar skeleton. And then there are the extreme examples, systems that reveal just how varied the UDG category is. Among the most famous is Dragonfly 44, or DF44. Discovered in the first wave of Dragonfly observations, DF44 immediately stood out as one of the largest and most structurally regular UDGs in Coma. Despite being extraordinarily faint, its diameter rivals that of the Milky Way. What truly shocked astronomers, however, came from its internal dynamics. When its globular clusters and stars were measured with instruments like the Keck Observatory, their motions suggested a dark matter halo far more massive than expected for such a faint galaxy. Some early estimates proposed that DF44 might be as dark matter dominated as the Milky Way itself, despite having 1,000th its stellar mass. DF44's survival in the harsh tidal environment of Coma reinforced that interpretation. A diffuse galaxy of such low stellar density should, in principle, be torn apart by the cluster's gravitational field. The fact that it remains intact implies a deep well of invisible mass holding it together. Later refinements softened some of the more extreme interpretations, but DF44 remains a prime example of what a failed giant might look like. A dark matter halo that began with the potential to form a bright spiral but never converted enough gas into stars to reveal its true scale. Not all UDGs share this trait. Some appear far more fragile, with lower inferred halo masses. These may be galaxies that were stretched by cluster tides or heated by repeated interactions. Their faintness is not primordial, it is evolutionary. The end state of a galaxy gradually dismantled by its environment. Others, especially those found in the field, show signs of ongoing star formation. gas-rich UDGs challenge the assumption that all diffuse giants are quiescent or ancient. They may be high-spin systems that never collapsed, or late bloomers that retained gas but remained inefficient at turning it into stars. The diversity across the UDG population is scientifically significant. A single mechanism cannot account for their formation. Instead, UDGs occupy a crossroads where multiple evolutionary pathways intersect. Their sizes do not uniquely identify their origins, nor do their luminosities. What ties them together is their surface brightness, and even that spans a wide range. When astronomers first plotted UDG sizes and brightnesses on familiar diagrams of galaxy structure, these objects spilled into regions of parameter space long believed to be unoccupied. They filled a void between bright giants and compact dwarfs. They blurred the simple correlation between scale and luminosity. They forced theorists to revisit assumptions about how galaxies form, how feedback operates, how dark matter halos evolve, and how environment shapes structure. And when you move through one, whether in simulation or imagination, the contradiction becomes visceral. The shape tells you giant galaxy. The glow tells you barely a dwarf. You wait for the structure to resolve into something familiar, a bar, a spiral arm, a dense bulge. But it never does. You're wandering through a galaxy that feels unfinished, stretched across tens of thousands of light years, yet containing only the faintest population of stars needed to reveal its boundaries. Ultra-diffuse galaxies redefine what a galaxy can be. They show that size does not guarantee luminosity. They show that evolution can stall, stretch, or starve a system in ways we never anticipated. They demonstrate that darkness itself can be structured, that the universe builds giants not only from light, but sometimes from the absence of it. A soft haze fills the frame again, but this time the faint light doesn't just suggest emptiness. It suggests mystery. Ultra-diffuse galaxies don't merely look unusual, they behave in ways that force astronomers to confront one of the most fundamental questions in modern astrophysics. How much of a galaxy's existence is written in dark matter? When UDGs first emerged from Dragonfly's images, the immediate reaction wasn't just surprise at their size or faintness, it was confusion about how they could remain intact at all. A galaxy stretched over tens of thousands of light years, but containing only a few 100 million stars, should tear itself apart under the slightest gravitational stress. And yet, many of them drift through dense clusters like Coma, one of the most hostile gravitational environments in the nearby universe, without falling to pieces. Something unseen must be holding them together. That suspicion became the starting point of the UDG dark matter debate. The first hypothesis was straightforward. Maybe UDGs are simply dark matter-dominated dwarf galaxies. Their large physical sizes don't reflect their true masses. Instead, they might be dwarfs that were somehow inflated, stretched outward by internal or environmental processes. If their stars are few but their dark matter halos are robust, the galaxy could survive tidal forces, cluster interactions, and the internal fragility of a diffuse structure. For such systems, the starlight would be misleading, an underweight tracer spread thinly across a massive but invisible backbone. But to test this idea, astronomers needed to measure velocity dispersions, the speeds at which stars or globular clusters orbit within the galaxy. These orbital speeds allow researchers to calculate the mass required to keep the system gravitationally bound. Higher dispersions mean higher mass. Lower dispersions indicate a system with little dark matter. The challenge? UDGs are so faint that measuring their stellar velocities is agonizingly difficult. Even with powerful spectrographs, the light from individual stars is often too weak to produce reliable measurements. Instead, astronomers turned to their globular clusters, compact star clusters bright enough for follow-up spectroscopy. Globulars orbit within a galaxy's gravitational well like bees circling a hive. Their motions reveal the depth of the unseen halo. This approach led to one of the most influential early results. the dynamical study of Dragonfly 44. DF44 was already unusual, a huge, faint galaxy in coma whose structure appeared surprisingly undisturbed. When Van Dokkum's team measured the velocities of its globular clusters, they found them whipping around at speeds far too high for a system with DF44's minimal stellar mass. The data suggested a total mass comparable to that of the Milky Way, implying a dark matter fraction of about 98% or more. DF44 looked like a failed giant galaxy, a halo massive enough to form a luminous spiral or elliptical, but one that, for reasons unknown, never produced many stars. This idea captured the imagination of astronomers. Suddenly, ultra-diffuse galaxies weren't just oddities, they were laboratories for probing dark matter halos in regimes where baryonic matter barely participates. If DF44 was representative of a larger population, UDGs might reflect a hidden pattern in galaxy formation, that nature sometimes creates giant halos without the stellar mass we expect. But DF44 was only the beginning, and the story soon became more complicated. Subsequent velocity dispersion studies revealed a wide range of masses among UDGs. Some, like DF44, appear extremely dark matter dominated. Their globular clusters and stellar velocities indicate massive halos with gravitational wells strong enough to hold the galaxies together even within the turbulence of cluster environments. These systems fit naturally into the failed giant category, large halos that somehow never ignited into bright galaxies. Others, however, show velocity dispersions consistent with normal dwarf galaxies. Their halos are modest, their gravitational binding weak, and their structures fragile. If these galaxies exist in the outskirts of a cluster or in the field, they can survive. But in a dense environment like coma, they should be ripped apart. And yet, some survive there anyway, raising questions about measurement uncertainties, observational limits, and the role of environmental processes in shaping galaxy structure. The diversity in observed dispersions forced astronomers to rethink the idea that UDGs represent a single class of objects. Instead, they may arise from multiple evolutionary channels, each producing the same observable characteristics, large size, low luminosity, through different pathways. One key channel involves tidal heating or tidal puffing. When a dwarf galaxy orbits within a dense cluster, the gravitational pull from the surrounding mass can stretch and heat it, redistributing its stars and expanding its radius. This process can create a galaxy that looks ultra-diffuse without requiring a massive halo. In such cases, the galaxy might be living on borrowed time. It is only temporarily intact, and over billions of years, it may eventually dissolve into the intracluster stellar population. Another channel involves feedback-driven expansion. If early star formation in a small galaxy triggers strong supernova winds, the energy injected into the system can push stars outward, decrease central densities, and inflate the galaxy into a diffuse structure. This mechanism is commonly studied in simulations such as fire feedback in realistic environments, which show that repeated cycles of gas inflow and outflow can gradually transform a compact dwarf into a large, faint system. These galaxies retain dwarf-like halo masses, but their stellar content is redistributed into an extended, low-density configuration. Then there's the high-spin halo scenario. In this model, a galaxy forms within a dark matter halo with unusually high angular momentum. Gas entering the halo spreads into a wide disk before it can collapse to star-forming densities. The result is a galaxy that is large from the very beginning, but remains faint because the gas never concentrates enough to fuel abundant star formation. These galaxies may have modest dark matter halos, but appear enormous simply because their formation environment scattered their baryonic content thinly across a massive footprint. The existence of multiple pathways explains why UDGs show such a large spread in velocity dispersions and inferred halo masses. It also supports a simple but powerful idea. Size alone does not determine a galaxy's nature. two UDGs of the same diameter can have entirely different evolutionary histories. One a failed giant, the other a puffed-up dwarf, another a primordial high-spin relic. Yet even with this diversity, dark matter halos remain the unifying theme. Whether a UDG survives or dissolves depends primarily on the depth of its halo. In clusters like Coma, only halos massive enough to withstand tidal forces can protect their stars from disruption. This explains why some UDGs look surprisingly regular and intact, while others appear stretched, torn, or asymmetrical. Environmental pressure acts as a filter, only the strong survive. To further complicate matters, some UDGs appear almost devoid of dark matter, the famous DF2 and DF4 systems that will appear later in this episode. Their existence, if confirmed, forces the opposite question. If some UDGs have far too little dark matter and others have far too much, what is the actual definition of a UDG? Is it a mass-based category, a surface brightness category, a structural evolutionary outcome, or something more subtle that bridges all of these? For now, astronomers classify UDGs observationally: large effective radii, low surface brightness, and dwarf-like stellar masses. But dynamical studies show that this appearance masks an incredibly diverse family. The dark matter debate is not a distraction. It is the central key to understanding how such galaxies come to exist at all. Dark matter halos define their gravitational boundaries. They determine whether a galaxy can survive near a cluster core. They influence how gas collapses, where stars can form, and how structures evolve. And they dictate whether a galaxy becomes a luminous spiral or a faint, ghostly UDG. In many ways, ultra-diffuse galaxies are extreme tests of the dark matter paradigm. They probe the limits of halo formation, star formation efficiency, and environmental survival. They stretch the standard lambda CDM model into corners rarely observed, and they force cosmologists to confront a long-standing truth. Galaxies are not merely the luminous structures we photograph. They are the visible signatures of a far deeper architecture, one built primarily from matter we cannot see. UDGs make that architecture unmistakable. They are galaxies whose light has nearly vanished, but whose gravitational footprints speak loudly. They are reminders that in the universe, darkness is not just an absence of illumination. It is a structure, a force, a framework shaping the evolution of everything we observe. DF2 first appeared as another faint ghostly smear, an ultra-diffuse galaxy in the NGC 1052 group, roughly tens of millions of light-years away. It looked much like its kin, large, dim, almost hollow. But when astronomers began measuring the motions of its globular clusters, something unexpected emerged. Their speeds were incredibly low, so low that the total mass inferred from their orbits seemed to match only the mass of the stars themselves. Nothing more. Virtually no dark matter. This was not a small discrepancy. It suggested a galaxy existing without the invisible halo that is supposed to bind every galaxy together. Dark matter is thought to form the gravitational framework that allows gas to settle, collapse, and turn into stars. Without it, a galaxy shouldn't form at all, let alone survive the gravitational tug-of-war inside a small group environment. Yet DF2 persisted, quiet, diffuse, and apparently missing the very ingredient that shapes the universe on the largest scales. The result immediately drew attention. For decades, every galaxy ever studied showed evidence of dark matter. Some, especially UDGs in the Coma cluster, seemed to contain enormous amounts of it, sometimes far more than their starlight implied. But DF2 appeared to defy that rule entirely. And just as astronomers were absorbing this possibility, another surprise appeared. DF4, a close neighbour to DF2, exhibited similar behaviour. Two galaxies in the same environment, both showing velocity dispersions far too low for typical dark matter halos. A pattern, not an outlier. All of the evidence hinged on the dynamics of their globular clusters. UDG stars are too faint to study individually. but globular clusters, dense, bright, and compact, orbit through a galaxy's gravitational field like test particles. Measure their velocities precisely and you reveal the mass of the system. In DF2 and DF4, the clusters glided rather than raced. Their motion suggested that the galaxy's total masses were not much larger than their visible stellar masses. If these measurements reflected reality, the galaxies had somehow formed or survived, essentially without dark matter. But this is where distance becomes critical. If DF2 and DF4 lie farther away, they are larger and brighter. Their globular clusters are more luminous, and their internal motions imply a dynamical mass far smaller than expected, pointing to a lack of dark matter. But if they are closer than originally calculated, then their inferred sizes shrink, their luminosities drop, and the same observed velocities become entirely consistent with a normal dark matter halo. One interpretation overturns a central pillar of modern cosmology. The other dissolves the mystery completely. That is why so much debate emerged around how far away these galaxies really are. Several teams revisited their distances using a variety of techniques: surface brightness fluctuations, red giant branch tip analyses, and comparisons with known group members. Some found evidence that DF2 and DF4 might be significantly closer than the first estimates. Others defended the original measurements. The disagreement wasn't academic. It was the difference between a galaxy without dark matter and a galaxy behaving exactly as lambda CDM predicts. Competing explanations quickly surfaced. Some argued that the galaxies were once normal dwarfs whose dark matter halos had been stripped away by gravitational encounters with the massive elliptical NGC 1052. In this picture, tidal forces remove the extended halo first while leaving the stars temporarily intact. Simulations show that such stripping is possible, but not easy. It requires finely tuned interactions and specific orbital trajectories. And it raises its own question. If such stripping occurred, why do the galaxies still appear dynamically cold and structurally stable instead of stretched and disrupted? Others focused on the possibility of measurement biases. Only the brightest globular clusters could be observed, and the sample size was small. If even one or two velocity measurements were skewed by contamination, background objects, or uncertainties in the spectral lines, the inferred dispersion would drop, and with so few data points, the result could be misleading. Reanalyses did adjust the velocity dispersions slightly upward, but not enough to remove the tension entirely, unless combined with a shorter distance. A more radical interpretation came from proponents of modified gravity. In frameworks like MOND, the internal dynamics of a galaxy depend on both its own mass and the gravitational influence of nearby massive objects. If DF2 and DF4 sit within a strong external gravitational field generated by NGC 1052, then their internal motions might naturally appear lower than expected without requiring dark matter at all. To supporters of modified gravity, the galaxies weren't anomalies, they were confirmations. But this interpretation only deepened the debate, since most astrophysicists still favor dark matter over modified gravity theories. As all these ideas circulated, the galaxies themselves remained quietly indifferent. They drifted through their small group environment, dim and diffuse, revealing just enough light to provoke arguments, but not enough to resolve them. Their shapes offered hints of past interactions, but not a clear narrative. Their globular clusters traced gentle orbits that could be interpreted as evidence of a shallow gravitational well, or simply misunderstood due to distance errors. Most astronomers today lean toward the idea that DF2 and DF4 do contain dark matter, but far less than originally expected, or that the most dramatic claims were inflated by uncertainties in distance and small number statistics. Others hold that the distance estimates supporting the original claim remain valid, and that the galaxies genuinely challenge lambda CDM. The disagreement has not fully settled. The broader lesson, however, extends beyond these specific galaxies. DF2 and DF4 forced astronomers to reckon with the limitations of their measurements and with the assumptions built into their models. They revealed how sensitive interpretations are to seemingly small uncertainties, and they showed that ultra-diffuse galaxies, far from being simple, low-density oddities, occupy a frontier where the relationship between visible matter, dark matter, and gravity becomes unusually delicate. Whether or not DF2 and DF4 truly lack dark matter, they achieved something rare. They made the invisible framework of galaxy formation visible by its apparent absence. By raising the possibility, however briefly, that galaxies might exist without the dark halos we consider essential, they sharpened our understanding of what dark matter contributes, how galaxies assemble, and how fragile our interpretations can be when dealing with structures at the very edge of observability. They remain quiet mysteries, floating in a small corner of the universe, continuing to ask the same unsettling question. What if the rules we believe are universal are more flexible than we think? Clusters are not gentle places. They are the busiest, most gravitationally violent environments in the nearby universe. Cities of galaxies packed together, stitched by dark matter, suffused with hot plasma, and full of interactions that can distort, strip, or even destroy entire systems. If you were to drift into the Coma cluster, one of the most massive clusters within a few 100 million light-years, you'd feel that intensity immediately. Galaxies whip past each other at thousands of kilometers per second. The intra-cluster medium, a vast sea of superheated gas at tens of millions of degrees, fills the space between galaxies with torrents of high-energy particles. Tidal fields twist and stretch structures constantly. In this chaotic environment, survival depends on gravitational resilience. And yet, floating within this maelstrom, you find ultra-diffuse galaxies, hundreds of them, quiet, ghostly, fragile-looking. At first glance, they seem impossibly delicate for such a harsh environment. But their abundance in clusters like Coma is one of the strongest clues to their nature. It tells us that whatever UDGs are, they are shaped, perhaps even defined, by the environments in which they live. The sheer number of UDGs in Coma was one of the most surprising outcomes of the Dragonfly surveys. Not a dozen, not a few dozen, but potentially more than 1,000 faint, extended galaxies lurking between the bright ellipticals and spirals. This density is not mirrored in the field, where UDGs exist, but are far less common. Something about clusters seems to encourage their formation, or at least their visibility. One reason is straightforward. Clusters capture galaxies from a wide range of environments. Over billions of years, groups and field galaxies fall into the cluster's massive potential well. As they enter, they encounter two major forces that reshape their evolution: ram pressure stripping and tidal interactions. Both play crucial roles in sculpting UDGs. Ram pressure stripping occurs when a galaxy moves through the dense intracluster medium. The gas inside a galaxy feels a headwind, a pressure that pushes against it, sometimes strongly enough to blow it out entirely. In Coma, galaxies are travelling through the cluster at speeds often exceeding 1,500 kilometers per second, roughly 900 miles per hour. At these velocities, the intracluster medium acts like a furnace wind. Gas gets stripped away, leaving the galaxy without the fuel necessary to form new stars. Once star formation shuts down, the galaxy fades, its stellar population aging into a dim, diffuse glow. This gas loss can transform a once normal galaxy into a ghost of its former self. Without fresh stars, the galaxy's luminosity declines. Without gas to collapse into new clusters, the density profile flattens. The galaxy drifts toward the ultra-diffuse end of the spectrum simply because it can no longer replenish the brightness it once had. Environmental quenching, shutting off star formation due to environmental conditions, is one of the primary mechanisms behind the low luminosity of many cluster UDGs. But that explains only half the puzzle. UDGs aren't just faint, they're big. Something must also enlarge them, or at least prevent them from remaining compact. This is where tidal forces come into play. In a cluster, tidal forces are ever present. A galaxy travelling near a massive neighbour or near the dense core of the cluster experiences differential gravitational pulls across its structure. These forces can stretch, distort, or heat its stellar distribution, a process often called tidal heating or tidal puffing. If a small or moderate mass galaxy is repeatedly stirred by tidal forces, its stars can migrate outward, expanding its effective radius. The result is a galaxy that becomes physically larger without gaining mass or luminosity. In a sense, tides can inflate a galaxy, pushing its stars outward as it absorbs gravitational energy. Simulations of galaxy clusters support this idea. When dwarf galaxies fall into a cluster, repeated tidal encounters can gently heat them, causing their outer stars to drift into extended orbits. Over time, the galaxy grows in size and becomes less centrally concentrated. Meanwhile, the intracluster medium strips away gas, ensuring that no new stars form to brighten the galaxy. The combination of expansion and fading naturally produces an ultra-diffuse structure. The Coma cluster, with its enormous mass and high galaxy density, is a perfect laboratory for such processes. Its gravitational field is chaotic enough to stir galaxies repeatedly. Its hot plasma is dense enough to strip gas efficiently. Its dynamical history is long enough that galaxies falling in billions of years ago would have had plenty of time to fade, stretch, and settle into their present ghostly forms. The UDGs that populate Coma may therefore trace the long evolutionary path of galaxies altered by environment rather than initial conditions. Still, not all UDGs can be explained by tidal puffing or environmental quenching. Some, like DF44, appear remarkably intact, with smooth, undistorted shapes and surprisingly large globular cluster systems. These characteristics hint at massive dark matter halos, which would allow the galaxy to withstand tidal forces without being torn apart. A high-mass halo provides a deep gravitational well that keeps stars tightly bound, even if the galaxy itself looks delicate from the outside. This is where the distinction between failed giants and inflated dwarves becomes significant. Both can appear ultra-diffuse, but their underlying structures differ profoundly. Failed giants form in massive dark matter halos. They have the gravitational potential to become large, bright galaxies, but never form many stars, possibly due to early gas heating, strong feedback, or inefficient cooling. Tidal forces in clusters would affect them far less, and they would retain their shape even in a chaotic environment. Their diffuse appearance is primordial, not produced by environmental sculpting. Inflated dwarfs, on the other hand, begin as modest mass galaxies but become ultra-diffuse through tidal heating and ram pressure stripping. Their halos are less massive, their structures more vulnerable. They can be puffed up by repeated interactions, and their low luminosity is partly a consequence of losing the gas needed for star formation. Clusters contain examples of both types, which helps explain the enormous diversity observed among UDGs. In Coma, some UDGs appear stretched or asymmetric, a sign of tidal processing, while others look smooth and relaxed, more consistent with massive halos resisting deformation. The environment creates them, preserves them, or sometimes destroys them. Then there is the role of environmental quenching, a process affecting nearly every galaxy that enters a cluster. Once a galaxy loses its gas, whether by ram pressure stripping or tidal removal, star formation stops. Over the next few billion years, the young blue stars die, leaving only older red stars behind. The galaxy fades dramatically. In many cases, a galaxy that once had a moderate surface brightness becomes ultra-diffuse simply by aging without replenishment. The stars spread, but the brightness declines. A once ordinary dwarf becomes a near invisible giant. One of the strongest pieces of evidence connecting clusters to UDG formation is their distribution. UDGs are most common in high-density environments, particularly near the outskirts of clusters where tidal forces are strong but not destructive. This intermediate zone provides just enough gravitational stirring to puff up galaxies without tearing them apart. It is a balance between survival and transformation. Another clue is the relationship between UDG survival and halo mass. In the core of Coma, where tidal forces peak, only the most massive halo UDGs remain intact. Fragile galaxies are shredded, their stars scattered into the intracluster light. Thus, the UDGs found near the core tend to resemble failed giants, while those in the outskirts may represent inflated dwarves. The environment becomes a selective filter, preserving only those with deep enough dark matter wells to withstand the cluster's violence. As you drift through the cluster, these dynamics become almost visible. Some UDGs hover like intact relics of some early cosmic failure, their shapes smooth and undisturbed. Others display faint tails or asymmetries, whispers of gravitational encounters that pushed their stars outward. Tidal scars linger, faint but diagnostic. Ram pressure stripping leaves some completely devoid of gas. Star formation has ended. What remains is the long echo of evolution in a dense environment. Clusters like Coma are enormous factories of transformation. They take incoming galaxies and reshape them, sometimes violently, sometimes gradually. Ultra-diffuse galaxies are one of their most striking products. They sit at the intersection of gas physics, dark matter dynamics, gravitational tides, and the slow fading of stellar populations. Their presence tells us that galaxy evolution is not solely an internal process driven by intrinsic mass or halo physics. It is a dialogue between galaxies and the environments they inhabit. In clusters, that dialogue is loud. UDGs are the faint signatures of that conversation, giant outlines of systems altered by forces far larger than themselves. They remind us that even in the brightest, busiest environments in the universe, some galaxies live quiet, dim lives. Not because they were born faint, but because the cluster taught them to fade. Ultra-diffuse galaxies are often associated with the dense, disruptive environments of galaxy clusters, where tidal forces, ram pressure stripping, and environmental quenching can transform ordinary dwarfs into large, faint systems. But the discovery of ultra-diffuse galaxies in the field, far from the gravitational turmoil of clusters, showed that these diffuse structures are not exclusive products of external processing. Some galaxies become ultra-diffuse even when evolving in relative isolation, where interactions are rare and the intracluster medium is absent. Finding these field UDGs required deeper surveys and more careful distance estimates, since faint extended objects in the field could easily be misclassified as small nearby dwarfs or background galaxies unless their true distances were known. One of the most important examples is UGC 2162, located roughly 24 million light-years from Earth. Unlike the quiescent, red, gas-poor UDGs commonly found in clusters, UGC 2162 contains a substantial reservoir of neutral hydrogen. Observations from AI surveys, including work associated with alfalfa, revealed that the galaxy's gas disk extends well beyond its already diffuse stellar distribution. This alone distinguishes it from cluster UDGs, which typically lose their gas soon after entering a dense environment. In UGC 2162, the gas remains intact, and patches of young stars indicate that star formation is ongoing, though at a low and inefficient rate. Rather than being a faded remnant, UGC 2162 appears to be a system that formed diffuse from the outset. The existence of gas-rich UDGs requires internal mechanisms to explain their diffuse appearance. One possibility is that they form in dark matter halos with unusually high spin. In such halos, angular momentum spreads gas over a large area before it can collapse into dense, star-forming regions. When gas density remains below the critical threshold for molecular cloud formation, star formation proceeds slowly and inefficiently. This naturally produces a galaxy that is large, faint, and gas-rich. High-spin halos have long been predicted to give rise to extended low-surface brightness galaxies, and field UDGs may be an observational counterpart of these models. Simulations also support another pathway. Feedback from early bursts of star formation can reshape a galaxy's structure over time. In the fire simulations, feedback in realistic environments, repeated cycles of gas inflow, brief star formation episodes, and energetic supernova feedback can drive gas outward, altering the gravitational potential and pushing stars to larger orbits. This process gradually expands the stellar distribution, leaving behind a galaxy with a large effective radius and low central surface brightness. Unlike tidal heating in clusters, this expansion is driven internally. A galaxy shaped by this process can become ultra-diffuse, even if it never experiences a significant external interaction. Observationally, field UDGs display a broad range of properties. Some show clear signs of rotation, suggesting they may be diffuse, extended disks rather than spheroidal systems. Others have irregular or patchy star-forming regions. Measurements of their gas kinematics sometimes reveal slowly rising rotation curves consistent with dwarf-mass dark matter halos. Their star formation histories tend to be extended or bursty rather than rapidly quenched, reflecting the gentle evolutionary conditions of low-density environments. The diversity in these galaxies points to multiple ways to produce a diffuse structure without the influence of cluster environments. Another intriguing aspect of field UDGs is that many remain inefficient at forming stars even when gas is present. In galaxies like UGC 2162, the gas surface density appears too low to trigger widespread molecular cloud formation. Star formation is observed only in localized pockets, where gas manages to accumulate temporarily. The overall star formation efficiency is low, and the galaxy evolves slowly. This inefficiency may persist for billions of years, allowing the galaxy to retain a large gas reservoir while building only a modest stellar population. Observational studies using ultraviolet and infrared tracers show that these galaxies often have specific star formation rates far below those of typical dwarfs with similar gas content. The structure of the gas also plays a role. In some field UDGs, high observations reveal that the gas is extended and flocculent with irregular density fluctuations. This patchiness prevents the formation of coherent spiral arms and limits the growth of star-forming complexes. In others, the gas disk may be thick, turbulent, or weakly supported against gravity, all of which inhibit efficient collapse. The balance between turbulence, feedback, and gravitational settling appears to determine whether diffuse galaxies can form molecular clouds at all. A few field UDGs are found in extremely isolated regions, areas of the cosmic web where neighbouring galaxies are hundreds of thousands of light-years away. These isolated systems cannot be the products of tidal heating or ram pressure stripping. Their diffuse nature must be intrinsic. This isolation strengthens the argument that internal processes, rather than environmental ones, can produce UDGs. Their dark matter halos, gas dynamics, and feedback cycles must conspire to maintain large, low-density structures over cosmic time. Field UDGs also inform theories about how galaxies populate different parts of the dark matter halo mass spectrum. Many appear to inhabit dwarf mass halos, not the massive halos inferred for some cluster UDGs like DF44. This distinction suggests that multiple evolutionary channels lead to similar observational outcomes. In clusters, the dominant pathway may involve tidal effects and environmental quenching. In the field, high angular momentum, low star formation efficiency, and internal feedback processes play larger roles. The overlap in appearance arises because the observational definition of a UDG, large effective radius and low surface brightness, does not specify the underlying mass or evolutionary history. The presence of star-forming UDGs in the field also provides constraints on the minimum conditions necessary for star formation in low-density environments. By comparing them with quenched UDGs in clusters, astronomers can separate the effects of internal physics from external suppression. For example, the low star formation efficiency seen in UGC2162 reflects gas densities below a critical threshold, whereas quenched UDGs in coma lost their gas entirely. This difference highlights how gas retention and gas density, not merely gas presence, control whether diffuse galaxies can sustain star formation. Large surveys and deep imaging continue to expand the known population of field UDGs. Instruments optimized for low surface brightness detection, including Dragonfly and modern wide-field cameras, are capable of uncovering diffuse galaxies that traditional surveys overlooked. As more examples are catalogued, patterns begin to emerge in their gas fractions, morphologies, and environments. These patterns reinforce the idea that ultra-diffuse structure is a common endpoint for galaxies near the threshold of star formation efficiency. In the broader context of galaxy evolution, field UDGs demonstrate that diffuse giants are not confined to the disruptive influence of clusters. They arise across a spectrum of environments, shaped by the interplay of dark matter, halo properties, gas dynamics, feedback strength, and the stochastic nature of star formation in low-density systems. Understanding their origins requires disentangling these factors, and field UDGs provide a crucial baseline for doing so. Ultra-diffuse galaxies are faint, sparse, and structurally fragile-looking, yet many of them contain an unexpected feature that immediately caught astronomers' attention: anomalously rich globular cluster systems. For decades, globular clusters, dense, ancient star clusters containing tens of thousands to millions of stars, have been used as tracers of a galaxy's total mass. Large galaxies tend to host many globular clusters. Small galaxies tend to host few. The relationship is not perfect, but it is strong enough that counting globular clusters often provides insight into the underlying dark matter halo. This is where UDGs become puzzling. Some ultra-diffuse galaxies appear to host more globular clusters than galaxies with 10 or even 100 times their stellar mass. Others host almost none. This inconsistency is not just a curiosity. It is a clue pointing directly toward the diversity of dark matter halos that underlie these faint systems. In a typical dwarf galaxy, 1 or 2 globular clusters would already be notable. A system with fewer than 100 million solar masses in stars might host a handful at most. But early studies of UDGs in the Coma cluster revealed something unusual. Even though these galaxies were incredibly faint, their globular cluster populations could range from a few to more than 20. These counts were unexpectedly high for galaxies with such low luminosities. It was a signal that something about their halo properties differed from ordinary dwarfs. The curiosity rapidly intensified when astronomers examined the cluster populations of specific UDGs in more detail. Among them, Dragonfly 44, DF44 stood out. The galaxy had already gained attention because velocity measurements hinted at an unusually massive dark matter halo, but its globular cluster system added even more weight to that idea. Deep imaging with the Gemini North Telescope and later analysis from the Hubble Space Telescope revealed that DF44 hosted a population of globular clusters far larger than expected for its low stellar mass. Estimates place the number of clusters between 60 and 80, values typical for galaxies with billions of solar masses in stars, not a few 100 million. For context, the Fornax dwarf spheroidal galaxy, a classic example of a low-mass system, hosts 5 globular clusters and is already considered exceptional. DF44 exceeded that by more than an order of magnitude. This abundance matters because globular cluster count correlates more tightly with the total halo mass than with stellar mass. In other words, the more globular clusters a galaxy has, the more massive its dark matter halo is likely to be, regardless of how many stars it contains. This relationship emerges naturally in simulations. Globular cluster formation occurs early, before feedback processes significantly alter the baryonic content of a galaxy. As a result, cluster populations preserve a memory of the initial depth of the potential well. When researchers applied these correlations to DF44, the implications were striking. Its globular cluster count suggested a dark matter halo similar to that of the Milky Way. Combined with its large radius and extremely low stellar density, the halo mass estimate aligned with the hypothesis that DF44 is a failed giant, a galaxy that began forming inside a massive halo but never succeeded in turning its gas into a substantial stellar population. Globular clusters provided an independent confirmation of what velocity dispersion measurements were already implying. They served as a cross-check, reinforcing the idea that DF44 and other massive halo UDGs represent a fundamentally different evolutionary pathway from inflated dwarfs. Their halos were simply too massive to have been stretched into their present form by cluster tides alone. But not all UDGs match this pattern. Some have very few globular clusters, consistent with dwarf-sized halos. These galaxies are likely products of tidal heating, ram pressure stripping, or feedback-driven expansion. Their sparse cluster populations point toward modest halo masses, and their diffuse structures must be maintained by internal processes or mild environmental interactions rather than deep gravitational wells. This wide range in globular cluster populations across UDGs demonstrates that the ultra-diffuse category encompasses multiple kinds of galaxies, unified by appearance but distinct in origin. The clusters help separate these subtypes. A UDG with dozens of globular clusters likely resides in a massive halo. A UDG with only one or two clusters likely inhabits a low-mass halo. The observational appearance, extended radius and faint luminosity cannot differentiate these situations, but the globulars can. The presence of large globular cluster systems in some UDGs also raises questions about how these clusters formed in galaxies with limited star formation. One hypothesis suggests that globular clusters form during brief, intense bursts of star formation early in a galaxy's evolution. If the galaxy's gas supply was later removed or heated by feedback, environmental effects, or reionization, the formation of ordinary field stars would cease, leaving the galaxy faint, while the globulars would remain as bright, dense relics of the initial burst. Another possibility involves hierarchical formation. UDGs with massive halos may have assembled from early overdensities where cluster formation was efficient, but where subsequent star formation cycles were suppressed. The globular cluster system would reflect the early phase of the halo's growth, rather than its later quiescence. Globular clusters also provide a way to infer how resilient a UDG might be in its environment. Clusters in galaxies with massive halos follow stable orbits, protected from disruption. In low-mass halos, the orbits are more easily perturbed by tidal forces. Observing the positions, distributions, and motions of these clusters offers insight into the gravitational stability of the host galaxy. In DF44, for instance, the clusters occupy orbits that suggest a deep potential well. In UDGs, closer to the cluster core, where tidal forces are stronger, clusters may appear offset or loosely bound, hinting at ongoing disruption. The globular cluster luminosity function, essentially the distribution of cluster brightnesses, can also serve as a distance indicator, helping confirm whether a faint diffuse system is genuinely large or simply nearby. This method has been used to refine distance estimates for both cluster and field UDGs, preventing misclassification and clarifying which objects are truly ultra-diffuse. In systems like DF44, the clusters provide one more key piece of information. They are often compact and distinct enough to allow spectroscopic follow-up even when the galaxy's field stars are too faint to measure. This enables dynamical mass estimates where direct stellar spectroscopy is impossible. The clusters thus act as both historical markers and present-day measurement tools. Taken together, the properties of globular cluster systems in UDGs help disentangle their evolutionary histories. Rich cluster systems point toward massive halos and failed giant scenarios. Sparse systems point toward dwarf halos and environmentally influenced evolution. Intermediate systems reflect a mixture of internal and external processes. Globular clusters offer a pathway into understanding the formation of faint, diffuse galaxies that would otherwise remain nearly inscrutable. They act as tracers of gravitational potential, indicators of early star formation, and probes of halo structure. Across the UDG population, they reveal that appearance alone is misleading. An enormous faint galaxy might be a giant in disguise, held together by a massive dark matter halo, whose presence is betrayed only by the compact clusters orbiting within it. Another galaxy of similar appearance might instead be a stretched remnant, its limited cluster population revealing a shallow gravitational well. The richness or sparsity of globular clusters becomes a key to identifying which scenario applies, providing a crucial tool for interpreting structures that emit too little light for traditional dynamical studies. Ultra-diffuse galaxies present a problem that has no single, simple solution. Their large sizes, low surface brightness, diverse environments, and varied mass estimates make it clear that they do not arise from just one evolutionary pathway. Instead, UDGs appear to occupy a structural category that many different processes can produce. Theories of their formation have expanded accordingly, each explaining a subset of observed properties. The challenge is not choosing the correct scenario, but understanding how several mechanisms combine to create galaxies that look similar but originate from very different histories. A major divide in the literature distinguishes between failed giants and puffed-up dwarfs. These two models represent opposite ends of the mass spectrum. Failed giants are galaxies that formed within massive dark matter halos, halos comparable to those of the Milky Way or other large spirals, but never converted much of their gas into stars. Puffed-up dwarfs, by contrast, originate in low-mass halos and become ultra-diffuse through internal or environmental processes that expand their stellar distributions. The failed giant scenario gained momentum after studies of systems like DF44 suggested extremely high mass-to-light ratios. High-velocity dispersions in their globular cluster systems implied dark matter halos far more massive than their faint stellar populations would suggest. In this view, the galaxy's size is not anomalous. It is exactly what one expects from a large halo. The anomaly lies in the galaxy's failure to form stars efficiently. Several mechanisms could inhibit star formation in massive halos, such as early gas heating, virial shock heating in massive halos, or feedback from an active galactic nucleus that prevents cooling. Once the gas reservoir fails to collapse and ignite substantial star formation, the galaxy remains faint while retaining a large gravitational footprint. Puffed-up dwarfs form at the opposite end of the halo mass scale. These galaxies begin as normal dwarfs, but become ultra-diffuse because their stars are redistributed outward. Environmental effects such as tidal heating and ram pressure stripping are major contributors in cluster environments. As a dwarf galaxy passes through a dense cluster potential, repeated tidal interactions stir its stellar content, heating the stars and pushing them into more extended orbits. At the same time, ram pressure stripping removes gas, halting star formation and allowing the galaxy to fade. The combination of expansion and fading produces a diffuse system. In this model, the halo remains small, and the galaxy's ultimate size reflects external processing rather than initial conditions. Isolated UDGs, however, complicate these two categories. Their mere existence implies that diffuse structure can arise without strong environmental influence. Internal mechanisms must therefore be able to produce UDGs in the field. One of the leading explanations is the feedback blowout model, supported by simulations such as fire. Early in a dwarf galaxy's life, star formation can occur in short, intense bursts. Supernova explosions from these bursts inject significant energy into the interstellar medium, pushing gas outward and temporarily altering the gravitational potential. As the potential fluctuates, the stellar component responds, gradually migrating into larger orbits. Repeated cycles of bursty star formation and gas blowout can expand the galaxy's radius over time, producing a diffuse morphology even without external forces. The feedback blowout model has observational support in field UDGs that show ongoing but inefficient star formation. Gas reservoirs remain present, but the surface density is too low to trigger significant star formation. The intermittent bursts seen in the star formation histories of some field UDGs match the episodic feedback cycles predicted by simulations. This mechanism can reproduce large effective radii and low central surface brightnesses in dwarf mass halos, providing a strong argument for internal processes shaping at least some UDGs. Another major internal mechanism is formation within high-spin halos. In the standard cosmological model, dark matter halos have a distribution of angular momentum values. Most galaxies form in halos with moderate spin, allowing gas to collapse into a relatively compact disk. But halos in the high-spin tail of the distribution spread accreted gas across much larger radii. Surface densities remain low, preventing the gas from fragmenting into molecular clouds and forming stars efficiently. The resulting galaxy evolves as a large, diffuse system from the beginning. This pathway naturally explains isolated, gas-rich UDGs like UGC2162, which have extended gas disks, low star formation efficiency, and radii that exceed those of typical dwarfs. High-spin halos also match theoretical expectations from lambda CDM cosmology. They do not require unusual feedback histories or environmental interactions, only the statistical variation in halo angular momentum. This makes them a particularly appealing explanation for UDGs in low-density environments. Tidal heating remains critical for UDGs in clusters. When a dwarf galaxy enters a cluster environment, it experiences tidal shocks whenever it passes near massive members or crosses dense regions of the cluster potential. These shocks inject kinetic energy into the stellar distribution, raising stellar orbits and decreasing central densities. Over multiple interactions, the cumulative effect can expand the galaxy significantly. Tidal heating can also explain observed asymmetries in some cluster UDGs, including faint tidal tails and irregular outer isophotes. The process does not require a massive halo, making it consistent with UDGs that appear to inhabit dwarf mass halos. The diversity of UDGs strongly suggests that multiple formation channels operate simultaneously across different environments. A UDG in coma with a massive halo and dozens of globular clusters likely followed a failed giant path. A UDG near the outskirts of a cluster with signs of disturbance likely formed through tidal heating. An isolated, gas-rich UDG with active star formation likely owes its structure to high spin dynamics or internal feedback cycles. The observational category of ultra-diffuse galaxy captures systems that look alike but differ enormously in their histories and halo properties. Large cosmological simulations have become essential tools for exploring these possibilities. The Illustris and Eagle simulations produce extended, low-surface brightness galaxies through combinations of feedback and halo spin. Although not originally designed to study UDGs, these simulations show that galaxies near the threshold of star formation efficiency can naturally evolve toward diffuse structures. They also demonstrate that environment can amplify these tendencies in cluster settings. The fire simulations provide particularly strong support for the feedback blowout mechanism. In fire, dwarf galaxies experience repeated cycles of star formation and outflow. Gas expelled from the central regions weakens the potential well, allowing stars to migrate outward. When gas cools and flows back in, the process repeats. Over time, this oscillatory behavior inflates the galaxy. Fire produces UDG analogues in dwarf mass halos without invoking environmental effects, matching observed field UDGs. Simulations of galaxy clusters show the complementary environmental channel. Tidal stirring of dwarf galaxies in cluster potentials expands their stellar distributions. Ram pressure stripping removes gas and quenches star formation, leading to faded, diffuse remnants. The combination of heating and quenching matches the properties of quenched UDGs in Coma and Virgo. The most successful models of UDG formation treat the phenomenon as the intersection of multiple processes rather than the outcome of one. High-spin halos create large, faint disks in low-density environments. Feedback cycles expand dwarfs from within. Tidal heating expands dwarfs from outside. Quenching removes the fuel that would otherwise raise surface brightness. Massive halos, in rare cases, fail to form bright galaxies, producing failed giants. The appearance of a UDG, large radius, low surface brightness, can result from any of these mechanisms or from combinations of them. Identifying which channel applies to a given system requires additional clues: globular cluster counts, velocity dispersions, gas content, environment, structural asymmetries, and star formation history. Simulations provide the framework for interpreting these clues, while observations continue to expand the known diversity of the UDG population. This theoretical landscape offers a coherent explanation for why UDGs appear in clusters, groups, and the field, and why their internal dynamics vary so widely. Ultra-diffuse galaxies emerged from obscurity as observational curiosities, but the moment astronomers began identifying their masses, distances, and environments, they quickly became more than faint structural outliers. UDGs now sit at a point where galaxy evolution and cosmology intersect. Their sizes, dynamics, and abundance touch on several pillars of modern cosmology: the structure of dark matter halos, the predictions of lambda CDM, and the physics of galaxy formation in low-density regimes. Because UDGs push the limits of surface brightness and baryonic efficiency, they expose areas where current models succeed and areas where they remain incomplete. One of the clearest contributions UDGs make to cosmology involves testing dark matter models. Their internal dynamics, halo masses, and survival in cluster environments provide direct constraints on how dark matter behaves on dwarf and intermediate scales. In the standard lambda CDM model, dark matter halos follow well-defined relations between mass, concentration, and abundance. Galaxies forming within these halos should exhibit mass-to-light ratios that reflect the balance between gravitational binding and baryonic processes. UDGs complicate these expectations. Some, such as DF44, appear to inhabit massive halos with surprisingly few stars. Their velocity dispersions and rich globular cluster systems imply dark matter halos far more massive than their extremely low stellar masses would predict. If these mass estimates are correct, such galaxies occupy halos that should have produced far brighter structures. Their existence therefore probes the lower boundary of galaxy formation efficiency, testing how ineffective star formation can be within large halos without contradicting cosmological predictions. At the opposite extreme sit galaxies like DF2 and DF4, which, depending on the adopted distance, appear to contain minimal dark matter. If confirmed, these galaxies would suggest that dark matter halos can be heavily stripped, or that baryonic systems can occasionally form in environments where dark matter contributions are suppressed. Both possibilities touch directly on cosmological assumptions about halo integrity, the behavior of dark matter in tidal fields, and the universality of the halo-galaxy connection. even if distance revisions eventually resolve the anomalies, the debates highlight how UDGs serve as empirical stress tests of dark matter theory. Low surface brightness surveys have also become an important cosmological probe because they fill in a part of the galaxy population that was largely invisible to earlier wide-field surveys like SDSS. Traditional surveys were optimized for galaxies with moderate to high surface brightness, leaving an incomplete census of faint extended systems. Without UDGs, the faint end of the galaxy luminosity function remained biased toward compact dwarfs, and theoretical predictions about galaxy abundance on small halo scales could not be fully evaluated. The discovery of large populations of UDGs in clusters and smaller populations in the field expanded the observed diversity of galaxy structures and provided new constraints for models that link halo mass to galaxy luminosity. In cosmological simulations, such as Illustri's Eagle and Fire, ultra-diffuse analogues appear under specific conditions, usually involving high halo spin, strong internal feedback, or environmental processing. These simulated systems help quantify how often diffuse galaxies should form in a lambda CDM universe. A key cosmological question is whether the observed number of UDGs matches the number predicted by simulations. In clusters like Coma, hundreds or even more than 1,000 UDGs appear to exist. Simulations suggest that this abundance is plausible if a significant fraction of infalling dwarfs undergo tidal heating, quenching, or expansion. However, the exact number of predicted diffuse galaxies remains sensitive to feedback models and environmental histories, making UDG counts a valuable calibration tool. Another factor that UDGs test within lambda CDM is halo occupation distribution, the statistical relation between dark matter halos and the galaxies they host. Bright galaxies tend to populate the most massive halos, while dwarfs populate low-mass halos. UDGs blur this relationship by occupying halos across a wide mass range, yet all sharing the same diffuse appearance. Their existence shows that halo mass alone does not determine galaxy size or surface brightness. Instead, galaxy formation efficiency can vary dramatically, with some halos producing nearly no stars while others convert gas into stars more readily. UDGs therefore reveal that galaxy formation at the low-density, low-efficiency end is far more flexible than previously assumed. This flexibility is especially important for understanding the stellar-to-halo mass relation, SHMR. UDGs with high halo masses but low stellar masses test the lower tail of the SHMR, constraining the degree to which galaxies can deviate from average relations. If too many failed giants exist, theories must explain why star formation stalls so dramatically in some massive halos while proceeding efficiently in others. Meanwhile, UDGs with dwarf-like halos test the threshold of gas retention and star formation under shallow gravitational potentials. These faint systems tighten constraints on how feedback operates in low-mass halos and help refine models of reionization suppression and early gas heating. The presence of UDGs also affects cosmology through environmental dependence. Their abundance in clusters suggests that structure formation in dense environments produces many more diffuse galaxies than isolated regions do. This environmental dependence aligns with lambda CDM predictions that clusters assemble hierarchically, capturing many low-mass halos that then evolve under tidal and hydrodynamic forces. However, the existence of field UDGs shows that diffuse structures can arise without external triggers, which simulations must also capture if they are to remain complete. The relative numbers of cluster versus field UDGs therefore provide constraints on how often internal processes alone produce large, faint galaxies. Another cosmological implication involves the distribution of angular momentum in halos. The high-spin model for UDG formation requires that a subset of halos form with significantly elevated spin parameters. Lambda CDM predicts that halo spins follow a log-normal distribution with a tail toward high values. the observed number of field UDGs can be used to test whether that tail is populated as predicted. If too many or too few UDGs exist, it could imply that the spin distribution, or its translation into baryonic structure, differs from theoretical expectations. UDGs also contribute to understanding baryonic inefficiency. Many simulations predict that low-mass halos should convert only a small fraction of their baryons into stars. UDGs exemplify this inefficiency, often retaining large gas reservoirs but producing only modest stellar populations. By examining the gas fractions, star formation histories, and metallicities of field UDGs, astronomers can test feedback prescriptions used in cosmological models. Accurately modelling inefficient star formation across cosmic time is essential for predicting the faint-end slope of the galaxy luminosity function and for understanding how galaxies populate the cosmic web. Finally, UDGs highlight the cosmological importance of low-surface brightness science. Until recently, most galaxy catalogues were biased toward brighter systems, leaving an incomplete picture of the mass and luminosity distribution in the universe. As telescopes like Dragonfly, Rubin LSST, and next-generation space missions expand low-surface brightness sensitivity, the census of diffuse galaxies will grow, providing more robust constraints on dark matter, feedback physics, and galaxy halo connections. In these ways, UDGs reveal not just alternative pathways of galaxy evolution, but also valuable information about the cosmological framework that shapes those pathways. In the next decade, ultra-diffuse galaxies will move from the margins of observational astronomy to the center of several major surveys. The combination of greater sensitivity to low surface brightness structures and deeper imaging over wider areas will expose far more of these faint systems than current catalogues contain. Telescopes designed for wide-field mapping will be particularly important because UDGs are not rare objects confined to clusters. They span every environment, and many remain undetected simply because earlier surveys were not optimized to see them. The Nancy Grace Roman Space Telescope will play a central role. Its wide-field imager will reach surface brightness limits far below those of previous space-based surveys, allowing it to map diffuse structures across large regions of sky with uniform depth. Roman's stable point spread function will help distinguish genuine ultra-diffuse features from scattered light or image artifacts, improving the reliability of UDG classification. It will also allow precise distance measurements through resolved star techniques in systems close enough for individual red giant branch stars to be detected. This will help eliminate distance uncertainties that complicate the interpretation of galaxies such as DF2 and DF4. Euclid, already in operation, is another key contributor. Its infrared imaging and spectroscopy will map large-scale structure out to high redshift, and in doing so will detect diffuse, extended galaxies at earlier cosmic epochs. Identifying UDGs at moderate redshift would reveal whether their formation pathways were already active when the universe was only a few billion years old. If high redshift UDG analogues are common, it would imply that low-efficiency star formation and high-spin halo formation are long-standing elements of galaxy evolution. If they are rare, environmental processes in clusters may play a larger role than internal physics. On the ground, the Rubin Observatory's LSST will push low-surface brightness science to an unprecedented scale. Its deep co-added images will allow identification of diffuse galaxies down to extremely faint limits across nearly half of the sky. LSST will increase the known UDG population by orders of magnitude, providing the statistical power needed to determine whether cluster environments truly dominate UDG production or whether field populations are more abundant than current detection limits suggest. The large sample sizes will also help clarify whether massive halo UDGs like DF44 are rare anomalies or represent a broader class of failed giants. These observatories may also sharpen the dark matter debate. More accurate velocity dispersions, better distance estimates, and deeper imaging of globular cluster systems will test whether dark matter deficient candidates persist under scrutiny or whether they collapse into the expected lambda CDM distribution once uncertainties are reduced. If even a small population of genuine low dark matter galaxies survives these tests, cosmological models will require refinement in how halos interact, strip, or couple to baryons. Conversely, if improved data confirm that all UDGs occupy conventional halos, the category will still remain essential for mapping the diversity of galaxy halo connections at the low luminosity end. As surveys uncover more of these faint extended systems, they will clarify how often galaxies form at the edge of star formation efficiency and how frequently internal or environmental mechanisms dilute stellar distributions into diffuse structures. Understanding why the universe produces galaxies that are large but nearly invisible will depend on connecting these emerging datasets to simulations that capture the interplay of halo spin, feedback, and environmental evolution across cosmic time.